In this video, I will discuss linear probabilistic modeling and how it can be used in engineering. Linear probabilistic modeling involves doing a simple linear regression and then accounting for the distance between a point x and the regression line. The data shown can have a true fit line placed on it, and the equation of this line can be found as y equals beta 0 plus beta 1x, where beta 0 is the y-intercept of the line and beta 1 is the slope. Linear probabilistic modeling accounts for the distance between x and the true fit line by adding a random variable epsilon into the equation. This makes the equation become y equals beta 0 plus beta 1x plus epsilon. This is referred to as the model equation. A few assumptions are made about the random variable epsilon. It is assumed to have a normal distribution such that its expected value is 0 and its variance is sigma squared. Another topic that comes from epsilon having a normal distribution is the expected value and variance of y. If we look at a location on the graph where x is an arbitrary value x star, the expected value for y when x is equal to x star can be symbolized as mu yx star. The variance of y when x is equal to x star is symbolized as sigma squared yx star. The expected value can be derived by saying that it is beta 0 plus beta 1 x star plus the expected value of epsilon. But since the expected value of epsilon is 0, the expected value of y becomes just beta 0 plus beta 1 x star. The variance can be derived similarly by saying that it is the variance of beta 0 plus beta 1 x star plus the variance of epsilon. But the variance of beta 0 plus beta 1 x star is 0, and the variance of epsilon is sigma squared, making the variance of y just sigma squared. One example of how linear probabilistic modeling can be used in mechanical engineering is when developing a stress-strain curve. A stress-strain curve consists of two regions, an elastic region and a plastic region. For most common materials, stress and strain have a linear relationship within the elastic limit. After the elastic limit, all deformation is plastic and no longer follows the linear relationship. For this example, let's look at the elastic region by itself. Experimental data for the elastic region is shown on the graph with the true fit line placed over top. The equation for this line can be determined. Notice that some of the points do not fall exactly on the line. This is due to error, which can be accounted for by the term epsilon. Engineers are generally interested in finding the slope of this line because it represents a physical quantity called Young's modulus. I hope after watching this video you know a little bit more about linear probabilistic modeling and how it can be used.